Mars once flowed with rivers and lakes teeming with the potential for life. Now it's a barren desert of rock and dust. What force could have drained an entire planet of its water, leaving behind only ghost rivers etched into ancient stone? The answer might lie not in geology, but in the unrelenting fury of the sun itself. For decades, planetary scientists have struggled to explain how Mars lost its once thick atmosphere and flowing surface water. Satellite imagery shows channels carved by water, sediment deposits, and ancient shorelines, clear signatures of a once hydrologically active world. But today the Martian sky is thin, cold, and dry. The most likely culprit? The solar wind, a relentless flow of high-energy charged particles hurled outward from the sun. Yet until now, no spacecraft had ever directly observed the specific mechanism behind this atmospheric loss. Theories abounded, but solid in situ data was missing. That changed with one mission and one groundbreaking discovery. Understanding this loss could also redefine what we consider habitable zones, not just around our sun, but across the galaxy. And it raises a profound question: how many Earth-like planets have already been stripped bare by their own stars? NASA's MAVEN mission, short for Mars Atmosphere and Volatile Evolution, was launched in 2013 and has been orbiting Mars since 2014. Its primary objective is to understand how Mars's climate changed from wet and warm to dry and frozen. Led by principal investigator Dr. Shannon Curry of the University of Colorado Boulder, MAVEN carries a suite of instruments that include magnetometers, particle analyzers, and spectrometers. These tools were designed to trace the escape of atmospheric particles into space and reconstruct Mars's climatic history. Unlike earlier orbiters that focused on geology or surface mapping, MAVEN was purpose-built to monitor upper atmospheric processes. Before MAVEN, theories about Mars' atmospheric loss were based largely on computer models and indirect evidence. The key question was not whether the solar wind had played a role, but how. MAVEN's unique polar orbit allowed it to sample different regions of the Martian atmosphere and magnetosphere over time, building a global picture of how space weather affects planetary atmospheres. On May 28, 2025, a landmark study published in Science Advances reported something extraordinary. For the first time, MAVEN had captured direct evidence of a process called sputtering in action. Sputtering is not simply erosion, it's a violent atomic ballet. When solar wind ions crash into Mars' upper atmosphere, they knock atoms like argon and oxygen into space. It's not just heating or dissipation, it's molecular warfare. It's a mechanical ejection of molecules like billiard balls scattering across a table after a single high-impact break shot. Over billions of years, this may have been the silent force reshaping an entire planet, quiet, persistent, and utterly transformative. Using two of its most advanced tools, the solar wind ion analyzer and the neutral gas and ion mass spectrometer, MAVEN collected detailed data on the behavior of argon gas, a noble gas that doesn't chemically react and therefore serves as a perfect tracer. Researchers noticed elevated concentrations of argon directly at the altitudes where the solar wind was most intense. This wasn't just suggestive, it was confirmation. The interaction followed the theoretical models perfectly, validating years of atmospheric simulations. Dr. Curry described the process with an analogy that's both simple and powerful. It's like doing a cannonball in a pool. The splash you make sends water flying everywhere, and that's what the sun is doing to Mars. The solar wind, traveling at speeds of up to 1 million miles per hour, carries the force to strip atmosphere molecule by molecule. But this wasn't the only surprise. The rate of sputtering wasn't just significant, it was staggering. During periods of heightened solar activity, such as solar flares and coronal mass ejections, the sputtering rate increased by up to 4 times. These solar superstorms would have bombarded Mars relentlessly in its early history, when the young sun was far more active. This means that Mars' atmosphere may have been stripped away much faster than previously thought, possibly within just a few 100 million years after the loss of its magnetic field. This realization upends previous assumptions about the tempo of planetary climate collapse. The result? A vicious cycle. As Mars lost atmospheric pressure, water on the surface became unstable and evaporated or froze. With less water and less insulation, temperatures plummeted. The once warm, wet planet fell into a deep freeze. Ice migrated underground or to the poles, and any chance of sustaining life at the surface vanished. One of the biggest revelations of the study was just how essential the interplay between atmosphere, solar wind, and magnetism is in shaping planetary evolution. Mars didn't die in a single moment. It faded, one ion at a time. It was a slow, invisible tragedy, unfolding in the thin veil of sky above a planet once brimming with possibility. This discovery reshapes not only our understanding of Mars, but our criteria for habitability across the cosmos. Earth is uniquely fortunate. It has a dynamic magnetic field generated by a molten iron core, acting like a protective force field that shields us from the sun's fury. Without it, Earth's atmosphere might have suffered the same fate as Mars. MAVEN's findings underscore just how crucial magnetic fields are in preserving planetary environments. This also raises pressing questions about the thousands of exoplanets we've discovered. Many orbit stars far more active than our Sun. Without magnetic fields of their own, could these distant worlds be slowly eroding into lifeless rocks, their atmospheres blown away by constant stellar bombardment? Even worlds that lie within a star's so-called Goldilocks zone could turn out to be sterile if exposed to intense space weather without protection. The MAVEN mission gives planetary scientists a powerful new lens to judge which of these exoplanets might still retain the conditions necessary for life, and which have already crossed the point of no return. The findings also refine our understanding of Mars' own timeline. Knowing the exact mechanisms and rates of atmospheric escape helps scientists better estimate when Mars transitioned from habitable to hostile. It suggests that early Mars may have been capable of sustaining life for a much shorter window than previously assumed. This adds new urgency to upcoming missions like the Mars Sample Return and future crewed exploration. If Mars did once harbor life, those clues may be hiding in the oldest rocks before the sputtering began. Mars's transformation is not just a story of planetary change, it's a cosmic warning. Even worlds that once held promise can fall silent under the slow violence of space. Thanks to MAVEN, we now know how that silence came to be. But in unraveling that silence, we also gain a guide, a tool set for identifying which planets might still whisper the songs of life. As we push deeper into the universe, seeking Earth-like planets, biosignatures, or even intelligent life, this knowledge becomes critical. The future of space exploration may hinge not just on where to look, but when. Stay curious, stay watching, and subscribe for more real, recent discoveries that bring the secrets of space into the light.